morning all of you students. So today welcome to again lecture series on TyBsc physics. And we want to see here our subject is solid state physics and we have to continue the first chapter. That chapter is the crystalline state and we have to see here, we have to interesting see here the main point, that is the different type of lattices. You have no idea basically what is meant by lattice. That is, lattice is considered the regular or periodic arrangement of indefinite constituent particle in the imaginary space, that is known as the lattice. And that lattice having different types, and that first type which I have considered here, that the previous lattice. That name of the scientist which is the previous, and that shown that 14 different network of lattices can be generated. Lattices can be generated in which the lattice point arranged in a 3D space, and that every network are such that each point has identical surroundings, and these are known as the previous lattice. So what is main point here in the previous lattice? That lattice point have each having a identical surrounding. This word is main point, that is having a identical surrounding, because we have to know that any geometrical shape, like we have considered circle, we have considered a cube or parallelogram, that have identical surrounding means that having many of plane sides or angle sides, number of planes are same or not equal, or number of angles. So that or vertices, whatever made of this structure that have surroundings, and similarly that in previous lattice that have identical surroundings means that lattice point having the identical surroundings of atoms, identical surrounding of lattice, of the vertices of the cube, or such that any geometrical shape, okay, or for example the parallelogram. So depends on this, we have to see that the different types of the lattices. So in two-dimensional space, so there are 5 different types of lattices, and that which can be generated using by the translation vector of the translation coplanar vector, that is vector A and vector B. That depends on these two vector A and vector B, that have different types of, that is 5 different types of previous lattice in two-dimensional space, and that we want to see here one by one. And that 5 different types of previous lattice in two-dimensional, that first type we have to see here, and that type is the oblique lattice. So first type of the two-dimensional previous lattice which is given is, first type is oblique lattice. Okay, so what is the property of this oblique lattice, which depends upon two vectors, that is vector A and vector B, or what is the relation between vector A and vector B, and what is the angle between the vector A and vector B, which is 90 degree, 120 degree are different for this degree. Depends upon this information we have to define here what is meant by the oblique lattice. So oblique lattice, which is considered as in this type of lattice, so in this type, first main important condition what is the vector, what is the relation between vector A and vector B. So that is considered here, that is vector A which is not equal to vector B. So that is main point, vector A and vector B which is not equal to, and the angle between A and B. So this is main condition, vector A bar is not equal to vector B bar, and the angle between A bar and B bar is not different. Angle between A bar and B bar is different from 90 or 120 degree. So the angle between A bar and B bar, A bar and B bar is different from from 90 degree and 120 degree. So this is main condition in oblique lattice, that is vector A bar, that is the length of coplanar vector, that is A bar, and B bar, that is length which is not equal, and the angle between the A bar and B bar which is also is different from the angle 90 degree and 120 degree. And this oblique lattice, the conventional unit cell is a parallelogram, and whatever this oblique lattice, the conventional unit cell is called parallelogram. Okay, so this is the main condition of the oblique lattice, and we have to see here the diagram of this oblique lattice considered as the parallelogram, that is vector A and vector B which is size is not equal, and angle which is different from the 90 degree and 120 degree. So consider this oblique lattice. For example, this is the vector A, okay, and for example this second vector which is considered as the vector B, and this vector A and vector B, whatever angle made up between these two vectors which is different from the 90 degree and 120 degree, and you know that this angle which is different from 90 degree and 120 degree. So we have considered this imaginary point, and we have to see this structure which is similarly like as a parallelogram. So that's why we have to say that here the conventional unit cell is called the parallelogram. So main point is here, in this type vector A is not equal to vector B, and the angle between A bar and B bar which is different from 90 or 120 degree. So that figure is 1.50 which is given is the oblique lattice. Okay, so we have to know or get clear idea. So what is meant by the oblique lattice? This is the first type of the Bravais lattice in two-dimensional. Now second type of Bravais lattice in two-dimensional, which is given as the square lattice. This is first type, which is oblique lattice, and second type main type in that 5 types, which is here given and here. So second type is the square lattice. Or here in oblique lattice, consider as the main condition A bar is not equal to B bar, and the angle between A bar and B bar, which is different from 90 degree and 120 degree. So in square lattice, the main condition which is given here, mod of A bar is equal to mod of B bar, and the angle between A bar and B bar, that is considered as theta, that theta is equal to pi by 2, and the conventional unit cell which is considered as a square, So we have considered, so in this type of lattice, mod of A bar is equal to mod of B bar. Okay, so that is the side or length of both vector which is same. And next condition, the angle between A bar and B bar, which is considered as theta, and that theta is equal to pi by 2, that is considered as 180, pi value is 180, and that 180 by 2, which is considered as 90 degree, and the conventional unit cell is a square. The conventional unit cell is square. So by two vector, joining two vector, whatever geometrical structure which is formed here, that is known as the square. So for example consider, so this is considered as the vector A bar. Okay, and the next vector which is considered as vector B bar. Okay, so that both vector which has the side or length is same. The angle made between vector A and vector B, which is considered as 90 degree, And this square lattice, consider this type, that is vector A and vector B, that vector A, mod of vector A is equal to mod of vector B, and the theta, that is between the vector, angle between the vector A and vector B, which is considered as pi by 2, that is we have to say that angle is considered as the 90 degree, and that conventional unit cell is nothing but a square, So consider this vector A and this vector B, that size of both vector or length of this both vector which is same, and the angle between, consider that this angle between both A and vector B, which is pi by 2, and if we see this geometrical shape, which is, or the conventional unit cell is nothing but the square. So that figure 1.16, which is considered as the square lattice, Now next main types of this two-dimensional Bravais lattice, which is considered as the hexagonal lattice, and this main condition between vector A bar and vector B bar is what, and the angle between this, that is the theta, which is what, so that information we have to see here. So next main type of two-dimensional Bravais lattice, which is hexagonal lattice. So third type, which is considered as hexagonal lattice, and this hexagonal lattice considered as in this type. So what is the relation between vector a bar and vector b bar? So that is mod of a bar is equal to mod of b bar. So that is, say, we have to say that the length of vector a bar and length of vector b bar, which is considered as same, that is vector a bar and vector b bar, which is same, and the angle between vector a bar and vector b bar, which is considered as theta is equal to 2 pi by 3. 2 pi by 3. So actually what is this angle 2 pi by 3, which is considered as 2 into 180 divided by 3. So 3 6 the 18, or this 0, that is 60, or that nearly equal to 120 degree. So that is, we have to consider as the angle between vector a and vector b, which is considered as 120 degree. So that theta is equal to 2 pi by 3. And in hexagonal lattice, the regular hexagon which is formed, and when all nearby lattice point about a given lattice, that point O, are connected is indicate, and the primitive cell of this hexagonal lattice, which is considered as rhombus of 120 degree angle. So that is considered here, the primitive cell is the primitive cell is a rhombus of 120 degree angle, is a rhombus of 120 degree angle. So this is known as the hexagonal lattice, and we have considered, for example, the angle between vector a bar. So for example, consider this is vector a bar and this is vector b bar. And again consider this structure, which is like the benzene ring, or a 6 corner having for this ring, called as the rhombus of 120 degree, and this all side which is from this center O, for the same side. And suppose we have to see that is the, suppose this vector a bar and this is vector b bar. So that angle between this, which is considered as theta, and the theta, which is considered as 2 pi by 3, and we have to know that, so that these all point which are connected from this O at the same distance. So we have to say that vector a, mod of vector a and mod of vector b, which is equal to mod of vector a is equal to mod of vector b, and theta is equal to 2 pi by 3, and that unit cell, that primitive cell, which is considered as rhombus of 120 degree. So this is the basic idea about the hexagonal lattice. Now next lattice of 2-dimensional, which is considered as the rectangular lattice. So next 2-dimensional Bravais lattice, which is considered as the rectangular lattice. And you know that the condition of the vector, that vector a bar and vector b bar, so that mode of a bar, mode of vector a bar is not equal to mode of vector b bar. That see the information here, that is the length of vector a bar and length of vector b bar, which is not equal, but consider as the theta, which is considered as the pi by 2, that is considered as 90 degree, and that rectangular lattice which is considered as the conventional unit cell, which is the rectangle. So see figure of the rectangular lattice, so that is considered as figure 1.18. so consider as, for example, this is vector a bar, vector a bar, okay, and we have consider, so this is the vector b bar, vector b bar, and you know that that condition, that a bar, vector a bar and vector b bar, which is length, is not equal, and the angle between this a bar and this b bar, that angle between this a bar and this b bar, which is pi by 2, that is considered as 90 degree, and that structure which is formed, and that structure which is considered as the rectangle, and that's why we have to say that the conventional unit cell which is considered as rectangle. So this is figure number 1.18, that is rectangular lattice, rectangular lattice. Next type of the two-dimensional lattice, which is considered as centered rectangular lattice, centered rectangular lattice. And in this type of lattice we have to consider again same idea, that is mode of vector a bar, which is not equal to mode of vector b bar, and theta, which is considered as pi by 2, and this when all nearby lattice points which is about the given points O are connected. So for example, consider here that vector a bar and vector b bar which is not equal. So consider that is, for example, this is the vector a bar and that is vector which is considered as the vector b bar. So that two vector, that is length, which is not equal, so that's why we have to say that mode of a bar is not equal to mode of b bar, and the angle between two coplanar vector, that is vector a bar and vector b bar, is nothing but theta equal to pi by 2. And if we connect this trajectory, so whatever point O, so that is we have to say that that is rectangle which is formed, and when all nearby lattice points about a given point, that is O, are connected. So these are the 5 different types of two-dimensional Bravais lattice, which is considered as oblique lattice, square lattice, hexagonal lattice, rectangular lattice, rectangular lattice, and center rectangular lattice. And we will see here the what is the condition for vector a bar b bar, and what is the angle between vector a bar and b bar which is made of is there. So this is the first type, that is the Bravais lattice, which is in the two-dimensional. Now we want to see here the next types of the lattice, which is considered as the B, that is the three-dimensional lattice, three-dimensional lattice. So that three-dimensional lattice, which is considered as the 14 different networks of lattice which can generated in three-dimensional space by repeated translation of coplanar vector, that is vector A bar, vector B bar and vector C bar. That 14 types of this Bravais lattice network, that types are grouped into the 7 types of the conventional unit cell, and that shown the angle which is given as the angle of alpha, angle of beta and angle of gamma, which is considered in the vector A bar and B bar. And here three main vector which is considered as vector A, vector B and vector C. So that in corresponding these three vector, three angle made of in between these, that is angle alpha, beta and gamma. So we want to continue here chapter the crystalline state, the crystalline state, and we want to see here the main point which is given as the different types of lattices, different types of lattices. And first point already we have to see in here, that is considered as two-dimensional Bravais lattice, that is considered as 14 different network of lattice point having the identical surroundings. And next type, that is B type, which is, and this two-dimensional Bravais lattices has 5 different type considered as oblique lattice, square lattice, hexagonal lattice, rectangular lattice, centered rectangular lattice, that are different types. And three second types, main types of different types of lattices, which is considered as three-dimensional lattice. Three-dimensional lattice, and this three-dimensional lattice having 14 different network type, which is considered as the repeated translation of three non-coplanar vector, repeated translation of in this type two-dimensional Bravais lattice, that is translation of coplanar vector to coplanar vector, that is vector A bar and vector B bar. But here the repeated translation of three non coplanar vectors, that is vector A bar, B bar and C bar, that is vector A bar, vector B bar and vector C bar. And we have to consider this 14 lattice, that types have 7 types of conventional unit cell, and the angle alpha, angle beta and angle gamma represent the angle between the vectors A bar and B bar respectively. So the angles alpha, beta and gamma, the angles alpha, beta and gamma is represents the angle between A bar, B bar and C bar respectively. Okay, so that A bar, B bar, C bar and alpha, beta, which are collectively known as lattice parameter, that is A bar, B bar, C bar and angle alpha, beta and gamma, which is considered as the lattice parameter and lattice constant of the unit cell. And we have see here that three-dimensional lattice, the rough structure which is given here. So consider that three-dimensional lattice structure, how it is formed or how it is drawn. So consider that three-dimensional known as the three axis. Consider here, for example, axis x axis, y axis, and z axis. So we have to consider here so that structure which is considered as three-dimensional space structure, so which is given as this is, for example, x axis, this is y axis, and this is considered as the z axis. Okay, and we have to see here that three non-coplanar vector, repeated translation of three non-coplanar vectors. So consider as this is the vector a bar, for example this is vector b bar, this is vector b bar, and this is vector c bar, and the angle made or angle between a and b, a and c, and b and c, which is considered as, for example, this is angle alpha, this is angle beta, and we have considered this is angle gamma. Okay, so these are three angles and three vectors which are collectively connected to each other, that is known as the lattice parameter or lattice constant. So this structure which is considered as three-dimensional lattice, that is figure 1.20, consider as three-dimensional lattice structure, three-dimensional lattice structure, and all crystal may be classified into the following types of the system, that seven system considered as cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. These are seven types of the system which is considered as three-dimensional Bravais lattice, which is formed by repeated translation of the non-coplanar vectors. Okay, so thanking of you, and now next lecture we want to see here that different types of this three-dimensional Bravais lattice, that system which is considered cubic, tetragonal, or something, that we want to see detail in the next lecture. Thanking of you.